All right, so today our idea is to do optimization, but it's from a different point of view. We're going to look at optimization when there are multiple variables involved. So we're going to start with the very first problem that I ever do in Calc 1 to kind of be able to develop what it is that we want to do in higher dimensions. So if I said, given a perimeter of, let's just say, 100 feet, construct a rectangle with the maximum area. Okay, this is usually the first one I like to do. This is what I did today in my Calc 1 class. So basically you have 100 feet of fencing and you want to build an enclosure, maybe a dog run or something, and you want it to be the maximum amount of area. So draw a picture of that. Okay, let's call that X and call that Y. So what I want to do is maximize area, which is the product of X, Y. Now, anytime you have an optimization problem, it usually comes with some form of a constraint. My constraint here is that I have 100 feet of fencing. See, X and Y cannot grow infinitely. So I am bound by this. So we'd say subject to, now if my perimeter is 100 feet, I know the perimeter of the rectangle, I just add up the sides. So 2x plus 2y equals 100. Okay, so I want to maximize that product subject to that. Now, are there any constraints on either x or y? Yes, because I only have 100 feet of fence. If I chose to use all of it for these two sides, each one could only be 50. Same thing, if I chose to use all of it for these two sides, each one could only be 50. And I cannot have a negative value. Okay, so we'll get to that in a moment. Now, this is Calc 1 for a moment. I know I have to take a derivative in order to maximize. This is the thing I'm trying to maximize. So that's the thing I'm going to differentiate. But in Calc 1, I cannot have two variables there. So what we did was we looked at the constraint and we solved for one of the variables. So let's say we want to solve for the y. So I'm going to substitute this y into this equation, and now I will have area strictly as a function of x being x times 50 minus x. Now I can put a constraint on x. We just said a moment ago, x can't be negative and it cannot exceed 50. So x would have to be between 0 and 50. That makes sense. That way, if I got a value outside of that range, I'd know it's extraneous. So the next thing we did, again, Calc 1, I'm going to multiply that out. So now we take a derivative. I set it equal to 0 and I get one solution. X is 25. Now, I don't know if this is the best case, this is the worst case, or maybe there's an inflection point there. I don't know, so I have to perform a test. I can either use the first derivative test, that's where I look for intervals of increasing and decreasing where it turned around. I can do a second derivative test. That's where I do the second derivative evaluated at the critical number and determine is it positive or negative. Or I can use the extreme value theorem because I have a closed interval. That's where I evaluate the endpoints and the critical number, and whichever is biggest wins. I'll use the second derivative test in this case. So my a double prime is -2. So a double prime evaluated at the critical value is -2, which is less than 0. So what that meant in Calc 1 is I am concave down where I have a horizontal tangent. That means it must be a maximum. If I were concave up, that would mean I had a minimum there. So x equals 25 gives the maximum area. And if x is 25, we notice that so is y. Oh my gosh, the maximum area will be when it's a square. Yeah, we kind of knew that. But that's how we showed it using calculus. We did all of this, but we first had to change it to a one variable problem. We will no longer have that limitation. Now, let me give you a simple example in baby algebra, remedial algebra. you did things like this. All right, at the theater, they sell child and adult tickets. And let's say the child tickets are $8 and the adult tickets are $12. At the end of the night, we sold 1,000 tickets and we had revenue of, $978. Can we work backwards and figure out how many of each type we did? Yes. So we said something like this. Let X be the number of child tickets. And I can't call Y the number of adults. So 1,000 minus X will be the number of adult tickets. And then I set it up and I did the problem. A little bit trickier setup. But then in second semester algebra, where you learn how to solve systems of equations, you can now do two variable problems. So you said, let X be the number of child tickets, let Y be the number of adult tickets, and then X plus Y is 1,000. And the setup was way easier, because you had this additional tool of being able to solve multiple variable problems. In fact, you could do 3 variable problems, and that's how you learn the matrix and things like that. Well, we know how to do the calculus of one independent variable in Calc 1 and 2. We now know how to do the calculus of more than one independent variable. So we're going to come back to this problem after we develop our multiple variable technique. So I wanted to start with this to give you a foundation. And again, this is optimization from a Calc 1 perspective. All right, so now we're going to get into the theoretical part, because we've got to derive. I'm not going to tell you how to do it. We're going to derive how to do it. All right, so here's what I want to do. I want to maximize or minimize. That means I want to find the extrema, maximize or minimize, or both, because I might have both a maximum and a minimum. Okay, some function, let's call it f of x, y, subject to a constraint with x and y. Now, the constraint might be that I have a line, I have a circle, I have some two-dimensional shape on the xy plane. That's my constraint. We're doing this right now with only 2 variables. Okay, so the picture will look like this. Okay, so first of all, I'm going to draw my constraint. My constraint will be this. This is the constraint. Now, as we already know, whenever I have a constraint with x and y, I can make everything on the same side of the equation, set it equal to 0, and then I can make it a 2-variable problem. So this constraint's going to be g of xy equals 0. And in other words, my constraint might have been, okay, you have to be on the line 2x minus 5y equals 3. Well, if that were the case, then I would make my g of xy 2x minus 5y minus 3. My constraint might be you have to be on the ellipse 4x squared plus 3y squared equals 13. In which case I would make my g of xy 4x squared plus 3y squared minus 13. We already know how to do that. My constraint right now is 2-dimensional, but by throwing everything on the same side and renaming it, then basically my constraint is this. So this is not new. So that's the first thing. So subject to the constraint is given. You don't figure out the constraint. So now I'm trying to maximize or minimize my thing. So let's suppose that it turns out that after I do my calculus, let's say that x naught comma y naught is the critical point. Okay, I take my derivative, I set it equal to 0. However I did it, I got that thing there, somehow or another. So in general, if I drew I have a position vector, let's say that right there, that's going to be r of t. Okay, so r of t is going to put me in every point. We know this is a vector valued function. So I can generate every point on my constraint with a position vector, all right, where r of t, as we know, is x of t, y of t, nothing new, okay? And let's say, so that ordered pair, by the way, right there, that would be the ordered pair just in general, x, y, but maybe it's right here. That's x naught, y naught. And that's where my best kind of work is going to happen. It's going to happen at that guy right there. So this very specifically would be r of t0. Now I'm going to define that. Because X and Y are my variables, but X of t and Y of t, so I can have R of t. So we're going to define X of t naught is going to be X naught. Y of t naught is going to be Y naught. Oh, okay. So on the XY plane thing, I've got an ordered pair X naught, Y naught. But it basically, when I have X and Y being parameterized as functions of t, then I have this situation here. That's not a stretch. I can do that for every ordered pair on the XY plane. I can redefine it, X as a function of t, Y as a function of t, and so on. So this vector would be R of t naught, where R of t naught is, of course, X of t naught, Y of t naught, and that is just X naught, Y naught. Okay, that's not really that interesting, but that's what we're saying right here. Now, at that point right there, I have a tangent line. Let's say the tangent, oh, actually, let me use the same color. I've got a tangent line that maybe goes that way. So that's R prime of t naught, but I also have a gradient vector, and we know that the gradient vector is orthogonal to the curve. Therefore, the gradient vector must also be orthogonal to the tangent vector. And that gradient vector would be the gradient of g of X naught, Y naught, because we're defining g with X's and Y's, we're defining R with T's. I know there's a little confusion, but it's X of t, Y of t. So technically you can think of this as X of t, Y of t, ultimately. All right, so I've got this really cool, beautiful, interesting picture. So now what? Okay, what am I supposed to do with all of this stuff? Well, here's what we do know, okay? We know that we've said, based on the calculus, that good stuff happens at this point. So I want those two vectors at that point. This was just the position vector in general. I could have done that at every single point on the blue curve here, okay? And we have this. Now I'm going to go ahead and erase. Now let's do a little calculus. All right, I said I wanted to maximize or minimize. I wanted to find the extrema of f of xy. Well, f of x naught, y naught is the extrema. Because we said x naught, y naught is where it's happening. Not because I'm telling you ahead of time, I'm saying it exists, and let's assume that we figured it out. We figured out where it is. Now, since technically, excuse me, since technically this is x of t naught comma y of t naught, I want to redefine this function f of xy, which is f of x of t, y of t. Technically, I want to redefine this as capital F of t. Much the same way we have a position vector that's made up of the little x and y. I have an f of xy, but if x and y are technically functions of t, then I want to just call this one big old function of t. Nothing wrong with that. Okay, and it's really simple to think about it in those terms. You see, okay, again, I want to keep it really simple because it seems like I'm making things up as I go. I kind of am. All right, so if x was, let's say, cosine t and y was t squared, and I said, all right, f of xy is 3xy squared. There's my function. Well, if I replace it with those guys, then it would be 3 cos t times t to the fourth. Oh, and I'll just call that f of t. Same thing, but now I've described it all in terms of t based on this. Okay, so no big deal. I want to take the derivative of that big F of t. So what does the derivative of big F of t look like? What is f prime of t? F's a function, it's not a vector. Well, according to our chain rule, it's going to be the partial of f with respect to x times dx dt. You could also say x prime of t, it's not going to matter. Plus partial of f with respect to y, dy dt. Okay, big deal. Now, what about f prime of t naught? Oh, if that was the extrema, then when I take the derivative and evaluate at that point, it has to be 0. So I know this has to be 0. But what is it? In this term, it's fx of x naught, y naught. I'm running out of room here. Actually, instead of dx dt, I'm going to write it as x prime. Then I can say x prime of t naught. It's the same. I was going to say dx dt evaluated at t naught plus fy of x naught, y naught, y prime of t naught. Okay. I just took this and evaluated it at the place in question. Remember, t naught comes from x naught, y naught. But in f, I want to leave it that way. And in terms of the x's and y's individually, I want to leave it that way. So what we have here is absolutely correct. But you know, that kind of looks like it's a dot product. I have a product plus a product. Could I write this as fx, x naught, y naught, comma, fy, x naught, y naught, dotted with x prime of t naught, y prime of t naught? I kind of got it. Okay. Could I write that as a dot product? Well, let's see. This product plus, yeah, I mean, that sure looks like that. But what is this? This is the gradient of f evaluated at x naught, y naught. Oh, okay. And what's this? That's, or actually, I'll write it. Instead of dr dt, I'm going to write it as r prime of t naught. Oh, that's this vector right here. Huh, that's interesting. When I redefined this guy as big F of t, and I took the derivative of big F of t, I got this. Great, that's chain rule. We learned that last week. Now, when I evaluate it at my happy point, the place I'm actually getting the derivative being 0, I get this. So in simple English, what does that mean? That means the gradient of f evaluated at the critical point, dotted with the tangent vector, is 0. That means they must be orthogonal. These two vectors have to be orthogonal. Well, why is that interesting? Because these two vectors were orthogonal. See, let's go back. Up there, didn't we already have that the gradient of g of xy dotted with r prime of t naught? Wasn't that also equal to 0? Because the gradient is orthogonal to the curve and the tangent vector is tangent to the curve. Why is this important? Because if both of these vectors are orthogonal to the same vector, then these vectors have to be multiples of each other. Oh, that's kind of huge, by the way. Gradient of f and gradient of g have to be multiples because they're both orthogonal to the same vector in 2 dimensions. That doesn't mean they have to point in the same direction. Right? They can point in opposite direction, but they have to be scalar multiples. And that's the key. That's our grand conclusion. Remember, I'm trying to find the extrema of f subject to the constraint g. So f and g are known at the start of the problem. And the way I'm going to find that is by actually setting an equation where they're equal. And the equation will look like this. The gradient of f, I'm going to set equal to a constant times the gradient of g. I'm just being shorthanded. Gradient of f of xy and g of xy. We now know they're constant multiples. Lambda is the constant. Lambda is called, more space, big drum roll, please. It's called the Lagrange multiplier. Okay, lambda is a Greek letter. It's the symbol we generally use in this case. It's called the Lagrange multiplier. It's how I can maximize or minimize things in higher dimensions. And it turns out what I just showed you, I can do for any number of variables. They just have to be in the same dimension. In other words, as long as f and g have 2 variables or 3 variables or 4 variables each, we can do this. We can do this in every dimension. It's crazy. We're not going to do it in every dimension. So the Lagrange multiplier. So now what I want to do is go back to the problem that we did with maximizing the area of the rectangle. Okay, so let's go back to that problem. So we wanted to maximize area equals xy subject to 2x plus 2y equal to 100. That was the problem that we started with. And we already know how to do it. We just used Calc 1. We had to solve for a variable and substitute it back and then do it that way. What if we don't want to do it that way? Like in intermediate algebra, when you could now handle multiple variables, you didn't need to solve and move things around. All right. This is, if you want to think of it as your F. So that's A of xy equals xy. And how about this? G of xy is 2x plus 2y minus 100. I now have two functions, each with two variables, and we will use the Lagrange multipliers. Now, I'm not saying this is superior to what you did in Calc 1. It's just an alternate way of looking at the same problem. And then that will allow us to do things in 3D. So what is the gradient of A? The gradient of A is partial with respect to x would be y, partial with respect to y would be x. What's the gradient of G? That'd be just 2, 2. And what we do is we say it like this. This is equal to lambda times this. And now, in essence, it really doesn't matter which side you put the lambda on. Lambda cannot be 0. But what's the other weird thing about this problem is you rarely are actually going to solve for lambda. It is rare that you actually calculate the value of lambda. You're not really interested in the value of lambda. You're interested in x and y. So where does lambda come in? Well, according to this, this means that y equals 2 lambda and x equals 2 lambda. So if I put those together, doesn't that mean x equals y? No, there's x and y are both equal to 2 lambda, so x must equal y. I really don't care what lambda is, but I'm using that as a vehicle to get to here. Oh, okay. So if x equals y, now let's go back to the constraint. Okay, so if x equals y, let me replace y with x, but not this version. This version, it's easier. So then I would get 2x plus 2y or 2x plus 2x because x equals y. So I've got 4x equals 100, so x equals 25. That was the answer we got before. Okay, but we had to do a first derivative test, second derivative test, extreme value theorem, whatever. Now, the question, how do I know this will produce the maximum? How do I know it's not something else? Well, first of all, Lagrange multipliers are guaranteed to give you an extrema. They're not guaranteed to give you a max. They're not guaranteed to give you a min. The problem that you have might only have a maximum or it might only have a minimum. It might not have both. Okay, but what you get will be always the absolute, because whenever you're subject to a constraint, that's kind of like thinking of a closed interval. You have to get an absolute extrema. So how do I know? Well, here's the simplest test of all. Take anything that satisfies the constraint, anything. Okay, but don't take 25, take anything else that satisfies the constraint. So just for the heck of it. So you said, all right, how about if x, by the way, and y is also 25 because x equal y. What if I said x equals 10 and y equals 40? That satisfies the constraint. Okay, that's not necessarily the best choice. I'm just finding something that satisfies the constraint. So now let's go back to the area. All right. So when x is 10 and y is 40, the area is 10 times 40 or 400. And I think it was square feet in this case. The values that I found were x equals 25 equals y. So the area is 25 times 25, which is 625 square feet. Here's the nicest thing about testing. If what I have is the absolute maximum, and I choose anything else that satisfies the constraint, there are an infinite number of combinations that satisfy the constraint. If what I found was the absolute maximum, then everything that satisfies the constraint will give me a smaller value. If what I found was the absolute minimum, then everything that satisfies the constraint will give me a larger value. That's it. There's no exception. So you test, generally speaking, you're going to need to test one solution to the constraint against yours. Now, I chose 10, 40. There were a couple more obvious ones. What if I had picked, I don't know, 50, 0, or 0, 50. I'm a big fan of using zeros, as many zeros as I can possibly use, because it's just less algebra. All right, so we have now figured out that the maximum area occurs here. And we did it because we had to do a test. That was my test up there. Now, we already knew how to solve this problem before as a one variable problem, and that's fine, but you can't always do that. So now let's move on and do some problems where they are already two variable problems, and it's not practical necessarily to rewrite. Okay, let's consider. We're done a couple of problems. Let's find the extrema and extrema is very generic. Technically, extrema is plural for extremum. Extrema means maxes or mins. Okay, so whenever you say find the extrema, you say, oh, this is my max, this is my min. Maybe I only have a max, maybe I only have a min. Maybe I have 3 places where there's a maximum, but I'm finding every place where there's a maximum or a minimum. That's what happens with extrema. Find the extrema of f of x, y equal to 4x squared y, subject to 3x plus 6y is 18. So I am maximizing this 3-dimensional function. And what I'm trying to do is I'm trying to find the ordered pair, the x comma y. Right. If without any constraint, basically every ordered pair on the entire xy plane could serve as input. Hopefully you all agree with that. Without any constraint, I could pick any combination of x and y and plug it in there. Piece of cake. But I'm saying, no, the x and y have to come from this equation. So in a sense, I do not have the xy plane as my domain. I only have the points on this line as my domain. Oh, so it may be that if I make x off the charts big, I'm going to make y off the charts negative. Ooh, and vice versa. So maybe there's a combination here that's going to make that, I don't know if it's the biggest it could be or the smallest it could be. I don't know. We'll have to figure that one out. Okay, so what we're going to do, first thing is we need to create the g function, and that comes from the constraint. So we will let g of x comma y equal 3x plus 6y minus 18. I don't actually need to write equals 0, that's implied, but there's my 3-dimensional variable. Now, the problem from here is pretty automatic. I want to write the gradient of f equals lambda times the gradient of g. That's the next thing I'm going to do. Okay, so the gradient of f would be 8xy 4y squared, and that's going to equal lambda times, now the gradient of g, that's easy, 3, 6. Usually the gradient that came from the constraint is a fairly simple notion. Now from there, I can write down the equations that I have. So from here,
simplify the g of x of y, because that's like reducible, but
yeah, it won't make any difference.
Okay.
Yeah, it won't make any difference in the long run. It is. The question was, could I make that a simpler statement? Sure. It won't save me any time though. That's the thing. Is it, in this case, if it made sense, then go ahead and do it, because it isn't going to change the answer. Because it's an equals, that's why. So here I've got 8xy equals lambda times 3, or I can just say 3 lambda. I have 4x squared equals lambda times 6, or 6 lambda. Now, here's the thing. I'm trying to find x and y, but lambda is also an unknown. So technically, don't I have 3 unknowns? I have 3 unknowns, and I should be able to solve this. But I have 3 unknowns, and it appears I only have 2 equations. If I have 3 unknowns and only 2 equations, if you've had linear algebra, you realize that could easily produce a dependent system and infinitely many solutions. Actually, no, I don't have 2 equations. I have 3. I have this equation. I have this equation. I have this equation. I actually do have 3 equations in 3 variables. Only 2 of the equations involve lambda, but there's a 3rd equation there. And I'm going to use this once I figure out the relationship between x and y. Now, I can't figure out the value of X and Y from here. I can figure out the relationship of X and Y from here. So you notice if I take the first equation, don't solve for lambda. No, make it easier. Take the first equation and just multiply both sides by 2. If I do that, now my first equation would become what? 16xy equals 6 lambda. Since they're both equal to 6 lambda, then these two must equal each other. That's how I'm going to solve it. So I now have 4x squared is equal to 16xy. Now that should not take me very long to solve. So 4x squared minus 16xy equals 0. Now I'm going to factor out of 4x, and that would leave me with that. So if I solve this, I have two possibilities. Either 4x is 0, in which case x is 0, or x minus 4y is 0, in which case x equals 4y. So it looks like I'm going to have two different solutions to this problem. And that's a good thing. We actually like it when we have two solutions, because in a Lagrange multiplier, when you get two solutions, one of them is going to be the maximum, one of them is going to be the minimum every time. All right, so let's see. Yeah, I'm not going to substitute quite yet. If x is 0, okay, let's figure out what it is. So if x is 0, then what must y be? If x is 0, then y must be 3. So my first ordered pair would be 0, 3. If x is 4y, if x is 4y, well, let's go back to here. Then I'd have 3 times 4y plus 6y equals 18. That's 12, 18, y equals 18. That would give me y equals 1. Okay, so if x is 4y, then y equals 1 and x would equal 4 times y. So my ordered pair would be 4, 1. Now quick check, 0, 3, oops, sorry, 0, 3, yes. 4, 1, yes, okay. So the two ordered pairs that are going to produce potential answers are 0, 3, and 4, 1. Now what am I going to do with them? I'm going to substitute them into the function that I am actually maximizing or minimizing. So let's start with f of 0, 3 is what? 0. Okay. F of 4, 1 is 4 times 4 squared times 1 is 64. Beautiful. Subject to this constraint that every ordered pair must be on this line. And you do realize if every ordered pair is on that line, then most of the time your ordered pairs are going to have opposite signs. The vast majority of the time. I'm sorry. They're not both going to be positive and they're not both going to be negative. They're usually going to have opposite signs. Yes. So it looks like, if I haven't totally messed this up, excuse me, this is going to be our minimum, and this is going to be our maximum. Try not to sneeze here. Okay, now a Lagrange multiplier is the link between two gradients, but it is not a value that is meaningful. There will be problems where you can find the Lagrange multiplier. It was really, really easy. It was just right there in front of you, but it's not something that you want to actually go out of your way algebraically to find. What you're using the Lagrange multiplier for is to connect the two, to relate the two together. All right, let's do another one, another two-dimensional problem. Then we're going to go to a three-dimensional, or I should say, sorry, not two-dimensional, I'm sorry, function of two variables and then a function of three variables. All right, so let's try another bad boy here. Let's say we want to, let me see if I can read my own writing here. Find the extrema of f of xy equals x times y, subject to x squared plus y squared is 8. Now my constraint in the xy plane is every point must be on that circle. So again, x and y cannot grow without bound. They are definitely bounded. So x cannot In fact, neither one of them could exceed √8 or negative √8 in size. So X and Y are probably going to be fairly small things. So I want to find the maximum and or minimum, whatever's available, of that function with that constraint. Okay. This is not going to be complicated, but it's going to be a little bit different than the last one. So we'll start by let g of xy equal x squared plus y squared minus 8. Now I have two functions of two variables and I can set their gradient vectors equal to a constant multiple of each other. So the gradient of f is what? Y comma x. The gradient of g is 2x, 2y. Now I'm not setting them equal. I'm setting the first one equal to lambda times the second one. That's important because lambda isn't necessarily 1. In fact, it's probably not going to be 1 pretty much ever. So now I've got, here's my equation. Now, because these are first degree, this is probably going to be pretty simple to solve for. So the first one says y equals lambda times 2x. The second one says x equals lambda times 2y. Oh boy, that looks confusing. Looks like I could go all over the map. And well, remember, I'm not looking to solve for lambda, and I really don't want quotients. I can manipulate this. I can say lambda equals, and set them equal to each other. But there's a much easier way. What if I said, let's multiply this? And how about multiply this? So, well, can't x or y both, can't either one of them be 0? Either one of them could be 0, but they both couldn't be 0. Ooh. So what does this tell me? xy equals this, xy equals this, so these two must equal each other. This is, here we go, sorry, 2x squared lambda, this is 2y squared lambda, and since lambda cannot be 0, and these two are equal to each other, I now have 2x squared equals 2y squared. Because these have to be equal, that means that x squared is y squared, or if you want x is plus or minus y. Oh. Yeah, I can have negatives. There's nothing wrong with negatives. Remember, I'm finding the extrema. Oh, so let's say x and y were opposite signs. Then I can have negatives. If x and y are the same sign, I have positives. I'm going to actually have several points. Let's see what I'm going to work right here. We've already got that down. So if x equals y, then what do I have? I've got x squared plus x squared equals 8. So 2x squared is 8. So x squared is 4. So x is plus or minus 2. When x equals y, x is plus or minus 2. So that means I've got 2, 2, x equals y, and negative 2, negative 2. Again, if x equals y and x can be plus or minus 2, I have these two ordered pairs at my disposal. But x could also be negative y. So let's look at that case. Actually, I can erase this now. So if x is negative y, then what do I get? I get x squared plus x squared equals 8. Oh, that's the same thing. Again, I get x equals plus or minus 2. Aren't I going to get the exact same points? No, x is negative y. Okay, so if x is 2, then y must be negative 2. And if x is negative 2, then y is 2. I have 4 points on the xy plane that will all contribute to the answer. 4 points. Interesting. Now, I don't know what the answer is. I have to substitute them back into the original function. So let's see what we got. F of 2 comma 2 equals f of negative 2 comma negative 2 equals 4. F of negative 2 comma 2 equals f of 2 comma negative 2. I can see that just by looking at it. So this is my maximum. This is my min. I have the maximum of 4, but it occurs at 2 places. I have a minimum of negative 4, but it occurs at 2 places. I don't say my maximum is 4 and my maximum is 4. If you remember back in Calc 1, basic graphing techniques, I can have a maximum occur at multiple points. There can only be one maximum value. If I said, the absolute maximum of my function is 10, well, it could happen many places. Think of a sine wave. On a sine wave, the absolute maximum is 1, but it happens infinitely many times. The absolute minimum is -1, but it happens infinitely many times. You can't have more than one value be the absolute maximum, but that can occur in more than one place. The absolute maximum is 4. It occurred in more than one place. Okay, so this one here was a little bit of extra work because I had many different places. Okay, that doesn't make it harder. It's just interesting. Now let's do one where I have more variables. So it's a little bit more to think about. All right, so sorry, I want to find the extrema. And I don't say find the max or min because I don't know ahead of time if it's going to be a max, a min, or both. So find the extrema of f of x, y, z equal x squared plus 4y squared plus 2z squared. Now, clearly, if x and y and z are just getting bigger and bigger and bigger and bigger, that thing's going to keep getting bigger and bigger. Whether they're positive or negative won't even matter. Oh, but wait a minute. Subject to, my constraint will make all the difference in the world. So subject to, hold on, what is my, can't read my own writing. 2x plus 4y minus z is 1100. Oh, that means all of my points must come from that plane. Okay, so I want to find the extrema. Okay, and now the thing is, I may only have one. So let's suppose I only get one. Well, then I don't know if it's a max or a min, so that's the one I'd have to test. Let's suppose I get two. One of them will be the max, one will be the min. I won't have to do any testing. That problem is a little bit easier. So now we need to create a function that satisfies our constraint. Because this is a function of 3 variables, now I need my g to be a function of 3 variables. So quite simply, I mean, that really just doesn't take a lot of thought, okay? Now, if you want, you can skip right down to the equation. There's nothing wrong with doing this. What is the gradient of f? I'm going to shortcut this one. The gradient of f is 2x, 8y, 4z. And that must be a multiple of the gradient of g, which is 2, 4, -1. So I saved a step by not physically writing gradient of f, gradient of g, but I still need that equation because that's where everything's coming from. You don't want to skip too much. So this says 2x equals lambda times 2, or if you'd like, just say 2 lambda. 8y equals 4 times lambda. 4z equals -1 times lambda. I think I can get all the lambdas by themselves on the right side. And if I do that, maybe I have a nice little link here. So for example, this one here says that x equals lambda. This says what? 2y equals lambda. And this here says -4 times z equals lambda. Is that useful to me? Yeah, that means x equals 2y equals -4z. Beautiful. And by the way, I still don't know what the value of lambda is. But if I use this information here, I may be able to substitute back in there. So the way I probably would be inclined to do this one is I would probably want to put everything in terms of y. And here's why. Here's why. I can write x equals 2y. And then here I can write, well, actually, maybe I should put everything in terms of, let's see, would it be easier to do x or 2y? So if x is 2y, and over here, oh, I got, and then Actually, I'm gonna do everything in terms of z. Sorry, I'm gonna use x equals negative 4z. It doesn't matter, but then I can say y equals negative 2z. I think that's, I don't want any fractions. I think that's the only way I can avoid fractions. Okay, because I know that is true. Okay, so again, 2y is lambda, negative 4z is lambda. Okay, so if I substitute these guys here, that's my equation. So I'm going to replace x with negative 4z. I'm going to replace y with negative 2z. Okay, and I think that's all I need to do in this case. So let's put those numbers in. So I'd have 2 times negative 4z plus 4 times negative 2z minus z equals 1100. So what does that give us? That's, if I didn't totally booger this up, I may have, I don't know. So 2 times, and where's x? X is negative 4z. Yes, so that's negative 8z. That's negative 8z minus z is 1100. So that's negative 17z is 1100. Yikes. Oops. 1100. So z is negative 1100 over 17. Ugh. But I can now easily tell you what x and y are. Okay, that's the easy part. Let's see, where can I do this? I think I can do this right. I want to make sure I have room here. Yeah, I can do this right here. I'll leave this here because I need that information. All right, so I've got z. So if x is negative 4z, then x is negative 4 times 1100/17, which is negative 4400/17. Y is what? Negative 2 times 1100/17, which is negative 2200/17. So in this case here, x and y, oh, did I? Oops, sorry. Z is negative, isn't it? My bad. Sorry about that. This should be negative. Negative. So these are both positive. Here we go. Okay, make sure I got that right. Okay, so I've got 4400/17, 2200/17, negative 1100/17. What am I going to do with that? I'm going to put it in here. If I didn't mess this up, I think I got everything. Okay, now I can erase this. F of 4400/17, comma, 2200/17, comma, negative 1100/17. Now let's get out our calculators. Okay, so 4400 squared plus 4 times 2200 squared plus 2 times 1100 squared. Oops, no, 1100 squared. Let's see, that comes out. Okay, good. So when I put that into my handy dandy calculator and I reduced it, this came out to be 242,000,017. Okay, that's what I got. I'd say that's a big yikes. Okay, that's a big yikes. That number's really big. Is that the absolute maximum? Is that the absolute minimum? That's really big. But maybe that's not the maximum. Maybe that's the minimum. I don't know. I need to test it versus any ordered triple that satisfies the constraint. Now, I mentioned before, picking zeros is always a really good idea. So why don't I use, as my tester, I'm going to use 0, 0, negative 1100. Use that as my tester. So now what is f of 0, 0, negative 1100? Now that answer on the board there, let me come back. 2, 4, 2, 1, 2, 3, 4. This number here is about 142,352.9. Okay, so it's really, really big. Now let's test negative 1100. This is, oh, quite a bit bigger. It's about 8 times bigger. In other words, believe it or not, that's our absolute minimum, not the maximum. You all wanted to say maximum because it was so big, but it's actually the minimum. Because when I took 1 point on the constraint, I took 0, 0, negative 1100, I'm sorry, 0, 0, negative 1100, and oh, you know what? My bad. I forgot to multiply it by 2. Sorry. It's 242,000. It's exactly 17 times bigger than this. Sorry. I said, yeah, I forgot to multiply it by 2. This dwarfs this number. This is my, and by the way, not this value here, 2,420,000 over 17. That's my absolute minimum. And you say, how could that be the minimum? This is actually easy to justify. X, Y, and Z can all grow positively without bound if you look at that. As X and Y get bigger and bigger and bigger and bigger and bigger, I'm going to need Z to get bigger and bigger and bigger to compensate because I'm subtracting it. So X, Y, and Z can all grow unbounded positively. So that thing there is going to grow unbounded positively. Oh, but if I'm going the other way, right? I want this to be the smallest total. The smallest total, strangely enough, is going to be at that order triple. It sort of defies logic at first, but this is the nature of the Lagrange multiplier. You never look at the value and say, oh, it's obviously a max or min. No, you have to test that value in this case. All right. So this is a good stopping point. Let me